if the characteristic equation is a polynomial that is derived for this type of equation by making an assumption as to what the solution, assuming the solution, supposing the solution has a specific form, right? So if that characteristic equation has roots alpha plus I beta, alpha plus I beta being a complex number, then the general solution takes form y equals C1 e to the alpha x cosine beta x plus, maybe I don't have enough room there, plus C2 e to the alpha x sine of beta x. Okay, so what we're saying here is that the solution of this second order here, this differential equation has derivatives of order up to 2, up to the second derivative, and the coefficients in front of each of these derivative operators are constants, here called a, b, and c. A, b, and c are assumed to be real numbers. When we transform this into making an explicit, assuming that the solution of this second order linear differential equation is exponential, we end up working with solving this differential equation is equivalent to finding the roots of a quadratic polynomial, a polynomial in R. When those roots are of this type, right? So this alpha here is the real part, and this beta is the imaginary part of these roots that are complex numbers, then those numbers, alpha and beta, play a role into the general solution of this differential equation. Alpha will be part of the argument of the exponential function. And beta, the imaginary part of that complex root, will be part of the argument of both cosine and sine. All right, so let's say, for example, so that here we have an exercise, and we want to solve y double prime plus 16 y prime plus 113y equal 0. And that we have initial conditions, y at 0 is 1, and y prime at 0 is also 1. So in second order, we are working with derivatives up to first and second derivative. The initial conditions involve the 0th derivative, the value of the function, and the first derivative, right? Two initial conditions because this is of order 2. So we're saying, you know what? Suppose that y has the form e to the rx. Y is e to the rx. Okay, r is a constant. And remember, this is we're assuming that this is y of x because this function, this ordinary differential equation that we have here is in terms of derivatives of y with respect to x, right? So if we make this assumption, then it's straightforward. We can compute the first derivative. This would be r times e to the rx. The second derivative would be r times what we had before, which means this becomes r squared e to the rx. And now we can go and replace in the original equation, right? So we had, let's call this equation number 1, for example. So now let's replace in number 1. Okay, so number one says we have 1 times the second derivative. So basically we have r squared e to the rx plus 16 times the first derivative. So this is 16 times r e to the rx plus this constant 113 times the original function plus 113 times e to the rx, and this is equal to 0. Right? So let's remember that the actual name of this differential equation here is second order linear differential equation, but specifically when this equation is equated to 0, this is called a homogeneous. This is a homogeneous problem, right? So we can factor that exponential function. The right-hand side is still equal to 0, and we're left here with r squared plus 16r plus 113. So you can see that there is a remarkable difference between this quadratic in r and this differential equation. It's almost like you replace the derivative operator with an exponent, right? Here's y double prime, or second derivative of y, and here is r squared. Here's 16 times y prime, 16 times the first derivative, and here we have 16 times r, and then there is that constant, you know, so you can think of this as y zero. The zeroth derivative means that you don't differentiate. The function stays as is, so that zeroth derivative is like a 0 exponent r to the 0, which is 1. So then both of these things are set equal to 0. We're interested on solving the equation. Exponential is not, as a function of x with any parameter, is not going to be equal to 0. So we just work with one of these factors. So we're working with r squared plus 16r plus 113 equal to 0. We want to solve this for, we're going to solve that equation for r, which means we're finding the values at which this quadratic is 0. And in general, those values are complex numbers. So we know from the quadratic formula, this becomes minus 16 plus minus square root, and here we're dividing by 2 times 1. This would be the square root of b squared minus 4 times this times that. So let me stretch this. So this is square root of 16, 4 times 1, and 1 times 113. Now, so at this point, we have basically transformed the equation in terms of derivatives. The solution of the differential equation is a function. We have transformed that problem into still an equation, but now this is an algebraic equation. It's about finding roots of a quadratic, right? So what will happen here is that, well, a couple of extra steps here is what's happening inside of this square root. This becomes 256, and 4 times 13 be 452. So this is looking like square root of minus 196, and this is plus minus 16. Okay, and that negative 116, you can write as that as minus 1. So you're going to have the square root of minus 1 come out, and this is multiplying the square root of 196. This is divided by 2, and here you have minus 16 divided by 2, and there is a plus minus there. Square root of 196, as this is a perfect square, so that becomes, this becomes I times 14 divided by 2. So remember, this is all about finding the values of r that make this quadratic in r equal to 0. So the so-called roots of this quadratic polynomial. So I'm going to call those, I'm going to give them a name similar to r, but I'm going to say that they are called, say, r1 bar and r2 bar. So I'm going to say that r1 bar is minus 8 minus 7 times I, and this one would be minus 8 plus 7 times I. You could also write this as minus 8 plus I times minus 7, and this minus 8 plus I times 7. You can write them both ways, okay? But the important thing here is that this number here is the real part. This is the real part of R1 bar. And this number here is the imaginary part of that complex number, okay? So, and these complex numbers are very similar to each other. The real parts are the same. In this case, they both have negative 8 as the real part. The imaginary parts are different only by the sign. One is positive, the other one is negative, but that's the only difference between them. These two complex numbers are called a conjugate, a complex conjugate group of two, okay? So when you find roots of polynomials, you're going to find that when those roots of polynomials involve complex numbers with non-zero imaginary parts, if the imaginary part is 0, that means the complex number is still complex, but is a complex number that lies on the real axis, right? Are you with me? Remember that the complex plane has an axis here, horizontal axis called the real axis, and then the vertical axis is called the imaginary axis. So for numbers that lie here on this horizontal axis, those numbers have imaginary parts equal to 0, and those are the typical numbers we call the real numbers. They're purely real. Now the analogy would be to some numbers that lie on this other axis, in which case those numbers have real part equal to 0, and they are called purely imaginary. The real part is 0, right? The fun thing is when those numbers lie in different parts of the plane here, this two-dimensional plane. So I was mentioning all this because what this theorem is telling us is that, look, you have a second-order linear differential equation with constant coefficients. A, B, and C are real numbers, or complex numbers with 0 imaginary part. A, B, and C are real numbers, yet you may find that the roots of the characteristic equation, which is, in this case, the characteristic equation is this polynomial, r squared plus 16r plus 113. Those roots may be non-trivial complex numbers or complex numbers with non-zero imaginary part. Question? Yeah.
So that step right there where you have y equals e to the rx, where do you get that from?
That's an assumption. The key is, where do I get that from? Is that I say suppose that.
Be part of
Suppose that. No, this is the procedure. The procedure is that you assume a specific, it's like, yeah, it's why do you suppose that? So if you know what the solution is, then why are you computing the solution? Well, yeah, it is kind of like that. I am supposing the solution is of a certain type. And I carry on here to give specifically what that type is. But this procedure in computing the solution assumes the solution has a specific form, and that form is exponential. But by assuming that this is exponential, the key is, okay, but it has a parameter, a constant r there, that we don't know what that constant is. So then this carries on, and then it becomes about what is the value of r? What is the value or values of r that we need to justify, yeah, the solution is of this form. So it is kind of, this is valid. This is a valid assumption whenever you have a differential equation of this type. Homogeneous, right. So constant coefficients, things that are multiplying the derivative operators, have to be constant, not functions of the independent variable. They have to be constant. And then you could, if you don't have a 0 there, it's still a second order linear, but it's not a homogeneous problem. But this procedure that we're talking about, assume the solution is exponential. That procedure applies when this is equal to 0, is homogeneous, and you have constant coefficients, right? But it's kind of, this is a good question, maybe. Where is that coming from? is kind of cheating, because you want to find the solution, but you're assuming what the solution is. But then why do you want to find it if you already know what it is? Well, I assume that it's of this type, but I need to find what R is to really say specifically this is the solution. Okay? So then there is more, because once we, in this case, have identified, look, R, these values of these roots of R have, they are complex numbers. So in this case, the solution, excuse me, the solution y of x becomes C1 e to the minus 8x cosine plus C2 e to the minus 8x sine. Okay, and that, what I'm writing in the argument of cosine and sine is going to involve the imaginary part. So this would be 7x, 7x. There. Now, so far so good, right? But is this really the solution? Remember, we, to your point, what is this business of e to the rx, right? Well, the solution we said, suppose, is e to the rx, but now we're saying, well, wait a minute, the solution is, there is some e, there is some exponential here, but this is multiplying cosine and sine. So is this e to the, how come this is e to the, how does this relate to e to the rx? How is this related to e to the rx? What's the cosine and the sine doing here? Exactly. So there are rumors coming from the back of the classroom here, and I hear these rumors, and they sound like this. Euler's formula. Dot, dot, dot. Euler's formula. Dot, dot, dot. So e to the I theta is cosine of theta plus I sine of theta. Thankfully, this formula is a big deal. This formula relates some of the most famous and important functions in mathematics. Even as a young student of mathematics, whatever your major is, right now you're a young student of mathematics. Okay? Young in the sense that you're in differential equations, and you're going to move on to Calc 3, analysis, some heavy-duty, juicy stuff, mathematical modeling, right? But even at this stage, you can identify e as being the exponential. That's a famous function. I being the square root of -1. That's another big deal. That's the whole algebra of complex numbers. On the right side, we have cosine. If you know cosine and you know sine, then you know trigonometry. Tangent and all that, yeah, whatever. But you need to know, it's like when you learn derivatives. You learn the derivative of cosine, you learn the derivative of sine, and then you need to know the product rule, quotient rule, and that takes care of like 2/3 of all the derivatives of a trigonometric functions, right? And the antiderivatives. So sine and cosine, big deal in terms of what trigonometry is. And this relates a way of writing a complex number in terms of cosines and sines, and how that is related to the exponential function evaluated at I times the angle here, or the argument, okay? So is in virtue of this formula that then is no surprise that e to the rx, the solution e to the rx, now that r, if I will, I can write here e to the alpha plus minus I beta x, and now this becomes e to the alpha x, e to the I beta x. So there is a portion of e to the alpha x there that's multiplying, and those sines and cosines may be coming out of e to the I beta x, exponential of I to the beta